Okay. Good afternoon, students. In the previous class, I hope my voice is audible and everything is visible, sorted. So let's start. Okay. Oh, let me check. Okay. So in the previous class, we have discussed about work done by variable forces, and how to calculate work done in these situations. So this was the last question that we were discussing. And there was a homework. If anyone done that, then please answer. Otherwise, I will move forward. Okay. So there is again, I have told you that why work done by variable force means a force may vary in two ways actually. One, in the way like we are saying that it is varying with the position. And second thing, it might vary with the uh, time. Depending on the time, it is varying. So this situation is the second case. Here they are asking, calculate the work done F by F in 2 seconds. In 2 seconds, you need to calculate the work done, and force is varying with the time. Force is varying with time. Okay, so let's try to solve it out. What we know that work done is actually work force is along the direction and displacement is also in the x direction. So I will directly write Fx dx. That's what we know. But in this situation, force is dependent on x, but we don't have the dependency of force on position. It depends on time. So what we need to do, we will need to do some other things like have a look at that. Force is given as 2t square. From the Newton's laws of motion, you can say force is equals to mass times acceleration. That is ma. 2t square. Nothing wrong with that. So if I say A will become, mass is given as 2 kg. So this 2 kg will cancel out with this 2. So A is equals to t square. Nothing wrong with that till now. We got acceleration is t square. Acceleration depends on time. Again, we will further write that. In the kinematics, you have learned that A can be written as dv over dt. This A can be written as dv over dt is equals to t square. So it will become dv is equals to t square dt. This is the old kinematics method, how to calculate the velocity kind of things. What I am going to do, I am going to transform the first equation. I will transform it. Okay. So if I integrate it, I will get V is equals to t cube by 3. T square integration is t cube by 3. We got t cube by 3. This is what V. Now, in this equation, if I divide by dt and multiply by dt, there will be no change in this situation. In the equation, there will be no change. You can see that. But this dx over dt will become velocity. Will become velocity. So it can be written as work done is equals to integration f dx over dt is v and dt. Force is given as 2t square. Velocity we have calculated as t cube by 3, and this is dt. Now my whole equation of work done is transformed in terms of time. My whole equation is transformed in terms of time. What we needed to done, we needed to eliminate this dx, because this dx is the small element in the terms of displacement. We need some time element. That's why we have done this term. Now it's very simple to calculate. We are asked to calculate the work done in 2 seconds. So limit will be 0 to 2. Now you can easily solve it. 2 by 3 is a constant. This term will be t raised to the power 5. If you integrate it, it will become t raised to the power 6 divided by 6. Limit is 0 to 2. Am I too quick to integrate that? T square into t cube means t raised to the power 5. If I integrate it, it will become t raised to the power 6 divided by 6. That will be 3. So I can write work done is equals to 1 by 9 t raised to the power 6, 0 to 2. If I put the limit, it will become 2 raised to the power 6. That will be 64 by 9 joule. This is the situation when force is varying with the time. What you need to remember for the rest of your chapter or rest of your till the exam, that dx needed to be replaced, and this could be done by placing a dt in multiplication and dt in divide, and for that we need dx over dt. So we have calculated that dx over dt. Okay, is that clear? I am moving further. If you have any doubt, you can ask me anytime. And I hope you are getting everything. I'm running quite slow as of now. Okay, moving further. Now, we have there is a punchline. Some punchlines what we have learned about the crux. I am going to write here. The crux is that you have learned that work done is f d cos theta for a situation like this. For a situation like this. This is force and this is displacement d. Now what I'm going to say, the first punchline, punchlines means important point that you need to remember is, in this equation fd cos theta, the term d is this is a very important line, very important application. The term d is the displacement that you usually say, but actually d is the displacement of that point where the force was applied. Are you getting this thing? D is the displacement not of the whole body. D is the displacement of the point of application of force. I will give you some example on that. Displacement of point of application of force. Listen to it once again. If you have a balloon, just assume a situation. You have a balloon like that. This is a balloon. And if I press it from this point, and suppose that this is being supported by some wall or anything rigid. This is not going to be anywhere. I just apply a very small amount of force with my finger on that. Then not the complete balloon will move. Only this part of the balloon will move. So not the complete body is moving. So when we calculated, when we apply this formula, we need to remember what? We need to remember that D is the displacement of the point of application of force, where the force is applied, how much displacement occurs in that particular point. Is it clear to you? First punchline was D is the displacement of what point. Second thing, what I say, I have told you, I think, this equation can be written as, I will change the pen. This equation can be written as W is equals to F cos theta into D. And F cos theta was the component parallel to the displacement. Force component parallel to the displacement. So we have, I hope I have told you that. Force parallel and displacement. This is second punchline. Now moving further, it can be written further as the third punchline. And third punchline is, can you write this equation again as work done is equals to F into D cos theta? If I take D cos theta, what is D cos theta? D is the displacement. This one is the D displacement. And if I take D cos theta, so D cos theta is this. Do you know how to take components, na? Nothing wrong with that, na? I hope you all know how to take the components of the vectors. So I'm not wasting much time in that. So if this is the displacement D, D cos theta will be this one. So D cos theta, can you say that force into D cos theta is parallel component of displacement? So you can also write it as force into D parallel. Parallel means displacement parallel to the force. Here, force parallel to the displacement. Are you getting these things? Three important points that I have told you. D is the displacement of the point of application. F parallel into D is another form of work done, and F into D parallel is another form. Now, fourth point is, this is fourth punchline, fourth important point that you need to remember, that work done is a property of frame. This is another very typical thing. Work depends on frame of reference. Do you remember in previous class I have told you two questions. Two questions of, one is truck was moving with a block on it, and another one is there is an elevator and it was going upward. In both the questions, have you noticed I have drawn an observer? I will show you. Like moving backward. Yeah, this one. In this question, I have drawn an observer. This one is the observer now. I have shown you the observer. In the previous question, I have also drawn, there is an observer, this observer. So this tells us that work depends on the frame of reference. If the observer was not there, it was in the lift itself, then for that observer, the block was not moving. If you are in a lift and lift is moving, the person in front of you isn't moving. So there is no displacement of the person and work done will be zero. So work depends on frame of reference. So work is not an absolute thing that every frame there will be the same answer. If observer changes its position, then work done will also change. Are you getting my point? If observer is sitting here, then according to him, the block is at rest. If the block is at rest, then it means there is no work done on the block. So work depends on the frame of reference. That's what I have told you. These 4 points are very important for us for moving ahead. I hope it's clear to you. You can at least write yes, no, whatever you want. Be proactive. Don't sit like a lazy boys. You can answer anything. Okay. You have chat box. You can answer. Okay. So there is a question on your screen. Let me explain the question first. There is a rod. This blue thing is the rod, linear, slim, thin rod, which is hinged by this point. Hinged means attached, freely attached, hinged by this point. And a force F is applied at the end of the rod. The rod, then what are they saying? Due to the force F, the rod becomes horizontal. If you apply, for example, this is the rod, which is hinged by this point, and you are applying force from the lower end, like this one. So they are saying that it becomes horizontal. It becomes horizontal. Is it visual to you, na? It becomes horizontal. So this is the situation from this position to this position. So what are they asking? They are asking us to calculate the work done by the force F. Work done by this force is to be calculated. Work done by gravity is to be calculated, and work done by hinge is to be calculated. So these are three important. What we have learned is going to be applied here. Okay. So do you want to try it, or I just move ahead? Okay. Let me solve it for you. First thing is calculate the work done by force F. We will focus on that only. First of all, I will draw the rod in the horizontal situation. It will look like like that. This will be the rod now. After horizontal becoming horizontal, force is this, and this rod is this. So if I calculate the work done by the force F, so what we have learned, FD cos theta kind of things, where D is the displacement, where D is the displacement in the direction of force. I have told you two things now. I have told you two things. Work done is force into D parallel or force parallel into D. We can use either of them depending on the situation, which is easier. We can solve, we can use that. So if I see the displacement of which point, point of application of force, this is the point of application of force, and this point moves from here to here. Am I right? The point of application moves from point A to point B. So this is the displacement that we need to discuss. But can I say that if I take displacement parallel to the force, if I take displacement parallel to the force, then it will be this displacement, horizontal displacement. No, you are not getting what I am saying. I am saying the actual displacement is this one. This is displacement, suppose D. I will solve it by that also. But what I am trying to say, if I check the displacement parallel, then this displacement parallel will be something like that now. This displacement parallel will be something like that. So this is the D parallel, and this is going to be a best application or to learn for the future. D parallel is, this is the displacement and this is the D parallel. And what is the value of D parallel? The length of the rod is L. So this distance is L. Again, this distance will also be L. So work done by the force is force into D parallel. And what is the value of D parallel? Is L. The answer is F into L. Okay, hold on. Is it understood by you? What I told you, if anyone can say yes, he can. Okay. JNV Vardha, JNV, what? Sangli. Is everything clear to you all? Okay. Now again, moving further. Work done by gravity. Second part is work done by gravity. So we need to identify where the gravity is. Do you know that gravity is mg and it acts downward and always act at the center of the body? Gravity acts at the center of the body. So gravity is downward mg and acting at the center. If I say rod becomes horizontal, then this center point is moved here. And again, the displacement is this one. Again, the displacement is this one because gravity is acting on this point and this point is moving to this point. So again, work done by gravity is, again, if I talk about force into D parallel. D parallel means parallel displacement, parallel to what? Parallel to the force. So force is, we are discussing about work done by the gravity. So which force we need to consider? We need to consider the gravity. So gravity is downward. So the displacement parallel to that. Is it clear to you that this point moves upward, is moving upward, and by a distance what? This distance is what? L by 2. Gravity center point was this one, where I am holding the pen. The pen is moved like that, rod is moving like that. The gravity point, the midpoint of the rod is moving upward, somewhat in. Okay, very good, JNV Sangli. Okay, so this point is moving upward. If this point is moving upward, what we need to consider, there are two displacement in this point. One, somewhat it has moved in the x direction and somewhat in the y direction. But what we need to consider, we need to consider the y component only. Why y component only? Because our force is in the y direction. Then the displacement I am considering is should be in the y direction because I am using the term F into D parallel. Are you getting these points? In this first situation, force was horizontal. So I was interested in the horizontal displacement. Now I am interested in the vertical displacement. Vertical displacement is what? L by 2. So answer is force is mg, displacement is L by 2. And the question is done. And again, there is a C part, work done by hinge. Work done by hinge, if you notice, this point is the hinge now. This hinge will apply if I hold this pen like that, then my finger must be applying some force on the pen. But what I'm saying, if this pen is moving like that, is the point of contact is moving. You can check that. Is the point of contact is moving? Is there any displacement of point of contact? If point of contact or point of application of force is not moving, then work done by hinge force is 0. What is the reason of that? Because displacement is 0. Of which point? Which point has zero displacement? The point of application of force has zero displacement. So what are the punchlines I have told you? All these punchlines are used here in this particular question. I hope everything is clear to you. This is a very good question. Mark it as a star because it will clear a lot of doubts of the work done. So now moving ahead. Spring force. Have you seen springs in your real life? Everyone has at least seen springs in somewhat in bikes used as a shocker or whatever you may call that, or you have seen springs in your chatpat type of fan like this one. There is a small spring in it. So springs is very famous, very common in our daily encounter. So how it looks like? This is a spring. Okay. So what we are going to talk about the spring is, first of all, the spring we are talking about is massless. Massless means we are considering its mass to be negligible. This is the first thing that we are not discussing in the is mass. Second thing, you notice that for example, a block is attached with it, and this time if I compress the spring, I have compressed it. Like from here, a person is pulling the block and he has compressed it. What he will feel? If you compress a spring, initially it is very easy to compress. But once you start compressing slowly, the force it exerts, it opposes the compression, and this force gradually increases. The same happens if you elongate the spring. If I elongate the spring, the same will happen if someone is pulling it like this one. Then gradually when he increases the length of the spring, he finds that the force, the restoring force the spring exerts is increasing. The opposition offered by the spring to the change in its position is known as restoring force or spring force. The first thing I told you, whenever you compress or elongate the spring, it exerts a force to oppose its change in position, and that force is known as spring force. This is the first thing that you need to remember, and you have felt that. I can say you have felt that if you compress the spring, it will exert a force to oppose your motion, to oppose your force, and this force is known as spring force. So what is spring force? The restoring force, I think the spelling is wrong, restoring force exerted by spring. इसको हम लोग डिनोट करेंगे किससे? Spring force. Force is F and S for spring. It is denoted by Fs. Nothing special in that. Now, there is a scientist, Hooke. He gave a law, Hooke's law. What he said? He says that spring force is equals to K times X, and he says minus K times X. So there are two things that you need to understand about this term. K is the spring constant and X is the displacement from mean length. Now this is again a new term, mean length. I hope you already know that, but still I am trying to say, if the spring is in relaxed condition, Relaxed condition, neither you are compressing it nor you are elongating it. Then the length of the spring is known as natural length or mean length. What we will generally use as natural length, or sometimes we call it mean length. So in this situation, the spring was not elongated. We have started pushing it, but not actually pushing it. So this position is known as mean position or natural length. So it is compressed by a distance x. So what is x? X is either amount of compression or the amount of expansion, stretching. How much you stretched or how much you compressed it. From where it is calculated? It is calculated from the natural length. So you clear displacement from the mean length. Okay, these two things are very clear. So what he says, the another term that we need to discuss about is the minus sign here. Now let me clear one thing to you. If you compress the spring, it will try to go away, try to remove your force. Like this, in this situation, first situation, this is the first situation, spring is being compressed, so spring will try to go back to its original position. It will exert a force outward, and this force is spring force, which is known as restoring force. Now in the second situation, this is the second situation, spring is being elongated or being stretched, so it will try to come back to its original position and it will exert force backward. These things that you can feel, actually it will try to come back to the original position. So what you have noticed, if I see that displacement is towards left, in this first situation displacement is towards left and force is towards right. In the second situation, displacement is towards right. From where we see the displacement? We see the displacement from the natural position, and from natural position displacement is towards right, so the force is towards left. So it shows me something, that force is always opposite to the displacement. So this negative sign indicates that Fs is opposite to the displacement. I think these three things are very clear to you. Now, can anyone tell me the unit of K? Unit of K. K is what? Spring constant. Can you find its unit? No? You can. Newton per meter. Is everything sorted? To summarize, if you compress the spring, it will pull you out. If you stretch the spring, it will pull you back. This is spring force. Done. Minus sign indicates that spring force is always opposite to the displacement. Now what I'm going to tell you, just focus on one thing. There are two things. In the future encounters, in the future conditions, like other questions, you have two options. Either you choose this negative sign to be put everywhere, or you need to decide the direction of a spring force. If you can decide the direction of a spring force, then this negative sign is not required at all, because this negative sign is put just to tell us that spring force is opposite to the displacement. If you can identify the direction of a spring force, then there is no need to put the minus sign. For example, I will delete it. For example, if I say, if I ask you basically that this is the spring, and this is its natural length. If I stretch it, I have stretched it to this point. Then what is the direction of spring force? Left or right? Can anyone answer? What is the direction of spring force? At least your voice should dominate your classroom actually. This is a small thing that you should answer, and your classroom should have, okay, there is the answer. Left, very good. JNV Daman has answered left, very good. So we can decide the direction now. If we can decide the direction, then I will not write as Fs equals to minus Kx. I will not write that. What I will write Fs equals to Kx, simply Kx, because I know the direction of force. And minus sign is just used to indicate the direction of force. So are you getting these things now? So now I am going to solve the work done by the spring force. Okay. So consider the situation that I have drawn here. Let's suppose the displacement is x. Displacement is x. The block is being stretched slowly from point O to point A. From O to A, it is being stretched slowly. So what we know that, let me know how many of you understood that this spring force is variable. Fs is equals to Kx now. Kx means it depends on x. As long as you are stretching it, the force is increasing because x is increasing. I think you got that point. So if I say that this is variable force, then work done will be what? Integration Fs dx. Why I am writing only x component? Because the force is acting along the x direction only and no component in the y direction. So I am not going to write that as well. Okay. So Fs into dx. From where to where you have displaced it? You are displacing it from, this is the mean position now. You can write it 0 or you can write it x initial, whatever you write it. I am writing it 0. Up to what point? Up to a displacement x. If this is 0.02 x. Now, this is the work done by spring force. F dot dx. Dx is the small displacement. Now again, if I say Fs is Kx dx, and can you tell me the angle between force and displacement? The block is being displaced from this position towards right, and spring force is acting towards left. So I know the direction. I know the two are opposite. So angle is 180. Angle is what? 180. Do you got that? Are you getting my point? Spring force is left, displacement is right, angle is 180, and cos 180 is minus 1. So minus can be brought outside. Minus k is a constant, can be written outside the integration, and the integration of x is x square by 2 with the limit 0 to x. So what it will become? Work done by spring force is minus half kx square. Work done by spring force is minus kx square. But you can remember the formula half kx square. That work done by spring force is half kx square. But you need not to remember the sign. You will not say, if someone asks you what is the work done by spring force and you are saying minus half kx square. No, this is wrong. It can be positive, it can be negative, it can be 0, depending on the situation, depending on the question. So you will not learn the sign. What you will learn the magnitude that work done by spring force is half kx square. It may be positive, may be negative, and sometimes maybe zero. Sometimes maybe zero. So the things are clear. So there might be a question that when, sir, it will be positive. Okay, when it will be positive. Okay, if I say, just I say that this block is released. If I say this block is released, then what will happen? This block will go back to the initial position. This block will go back to the initial position. Who is taking it back? I have left it. I have nothing to do with it now. I have left it. Who is taking it back? The spring force is taking it back. Spring force is left. Displacement of the block is left. Both are in the same direction. Then work done will be positive. Work done will be positive. So, are you getting this thing? That work done will be positive. So, what we have learned, spring force, who has given the formula? Hooke's law. Hooke's law says spring exerts a force Fs equals to minus kx. Minus shows that force is opposite to the displacement. We need not to use the negative sign, because if we can identify the direction of a spring force, there is no need to put the minus sign in the spring force. That is required for the ME persons need that minus sign. So now moving ahead. Okay. This is, I think, a double slide. Okay. So this is a good question on your screen. Have a look at that. Okay. Okay. If a variable external force, have you read the question now? Variable external force is applied slowly till the spring comes to its relaxed position. Find the work done by spring force. Now let me explain the question to you first. This is an inclined plane and there is a spring like this one. First thing that I need to ask, if you consider this system of spring and block, what you say, is this spring in its relaxed situation or is it compressed? I hope you all understand that if a spring is placed like that and a block is residing on it, then the spring will get compressed. So the picture in the diagram shows that spring is in the compressed mode. Are you seeing it? The spring is in compressed mode. So it is already in compressed mode. Very good. Someone has answered compressed. Very good, JNV Daman. Everyone should answer now. It shows that you are watching. Very good. Spring is in compressed mode. Now, what are they saying? If force is applied slowly till the spring comes to its relaxed position, now they are applying force to make it, to reach it to the relaxed position. So they need to apply the force here. If it is compressed, then to bring it back, they need to apply the force upward direction. So the external force is applied in this direction. Okay. And they are asking the work done by spring force. If I pull it upward, if I pull the block upward direction, then spring will exert a force in the downward direction. This is what spring do. So spring force will be in the downward direction. This is the thing happening. Okay, two things we have learned. Now, what is the work done? Work done is again integration Fs into dx. Fs is the spring force, dx is the displacement. Now we need to put the limits from where it is being displaced. What is the amount of displacement? So for that, we need to know that the displacement. Can I say that they are bringing it from the compressed position to the along to the natural position? So the amount it was compressed already is going to be the displacement. If I say that spring is compressed by the block by 10 centimeter and I need to bring it back to the natural length, so I need to displace it by 10 centimeter. So the displacement is what? The amount of compression already it has. So now I will try to find out the displacement. Okay, now consider the situation very carefully. If I consider the block, block will have AMG. You all know that. If I can omit other forces, like there is a normal reaction and there is a mg cos theta and there is a mg sin theta. Is it clear? There is a mg sin theta. So I am drawing it again. Actually, this is going to be worse for you. Okay. I can draw it here. This is theta. I am drawing it for initial condition, initially, when the external force was not applied on it. Then you can notice that there is a mg, there is a normal reaction, and you can tell me whether you know how to draw the FVD. If you don't, if you have any problem, I will help you out in that. This is mg cos theta. This is mg sin theta. Are you sure that spring is initially compressed? Then if spring is initially compressed, then it must be applying a force in the upward direction. This is what we are drawing the initial situation. So spring force is upward and mg sin theta is downward, and spring is now at equilibrium. If the block is in equilibrium, then you can say that this spring force is equals to mg sin theta. Now, if this thing is clear, spring force is what? Spring force is kx is equals to mg sin theta. Then the displacement x is equals to mg by k sin theta. This x is the initial displacement. This x is the initial displacement of the block. Now going back to the original diagram, that what we need to do, we need to pull it upward. So if we pull it upward, then spring force will be downward. Then spring force will be downward. So now if I calculate the work done by the spring force, then work done by the spring force W is equals to integration. Spring force is again kx, displacement is dx, and there will be a minus sign because displacement is upward, spring force is downward, so cos 180 is minus 1. What are the limits? What are the limits? It will become minus half k x square limit. Like this one. It will be moved to here. From this position to this is original 0 position, and this is x that we have displaced it. And what is the value of x? Value of displacement is what? Displacement is x now. And what is the value of x? We have calculated that. We have calculated that, put the value of x, w is equals to minus half k, and x is what? If I square it, it will become mg sine theta square divided by k square. Okay, I will increase the darkness of the pen. Okay, sure. Mhm. Can I change the color only? I don't know where is the option to increase the boldness of the pen. So if I change the color of the pen, will it work? The remaining part is the answer. That remaining part is if I write it somewhere, minus 1 by 2 mg sine theta square divided by k. This is going to be the answer. Minus 1 by 2 mg sine theta square divided by k. This is our answer. Okay. So this is a very good question. What we need to do, what we learned from this question is, okay, if I ask you, if you ask yourself what you have learned from this question, two things that I can say you need to learn. One is, it is not necessary that spring initially is in original position, is in natural position. It might be possible that spring initially is not in its original position, not is in natural position initially. I can show you like here. If I say that there is a spring attached with a block like that, M. Can you say that this length is its natural length or some extended length? You can say, sir, not in natural length. JNB Daman, is it visible now, or should I do something else for that? Or should I ask for some help? Actually, is it visible to you now? It is actually elongated now. Due to the gravity, it might be elongated. So we have learned that not necessarily spring in its natural length initially. Second thing, direction of spring force and the calculation of work done. This is the second thing. Okay, moving further. This is again a general topic, not a topic related to work done only. It can be applied anywhere. It can be applied anywhere. If I say, like there is a graph of force and displacement, F versus X graph is there. If we plot a graph, whatever maybe the graph, if I say that if graph is found to be like that, this is the graph between force and displacement. Then what I am saying, we have learned that work done is integration F dot dx. This is what we have learned. Dx is what? Small displacement. If I take a very small displacement dx on this x-axis, like this one, then during this small displacement, this force may be considered positive because the displacement is very small and force is varying with the displacement. So during the small displacement, variation in the force may be considered uniform and no variation can be assumed. For that situation, this F into dx is this side and F is the height. F is the height. Can you say that F dot dx is the area of the small strip? Here, F dot dx is what? Area of the small strip. This F dx is area of a small strip. If I take a lot of small strips like that, then on integrating it, I will get the area of the complete portion. Then I will get the area of the complete portion. So this F dot dx is what? Integration F dot dx is what? Area of the curve under the graph. Area of the curve under the graph. This is what F dot dx mean. So whenever we are asked to calculate the work done from a graph, what we need to do, we need to calculate the area under the graph. Now, there is a situation, there is a condition that you need to calculate the area with the x-axis. For example, if I say a graph between force and x is given like that, something like that, might be like that. Okay. So if I ask you, calculate the work done by this force, then which area would you calculate? This area or this area? This is area 1, this is area 2. Which area will you calculate to get the work done? Someone has answered. JNV Daman says area 2. Okay, anyone else? Okay, remember one thing. That's what I am going to tell you. Remember one thing. This equation itself tells us that work done is F dot dx. Okay, someone else is answering. Sorry, one. Okay, that's the right answer. So what we need to do, the term which is carrying dx, area should be calculated with that axis. So which is carrying dx term, d term. Like, so here we need to calculate the area with the x-axis. So remember one thing, area with x. X what? Displacement, not x-axis, horizontal axis. Area with x means displacement. If I ask you a simple general question, not of the work done, do you know that velocity can be written as dx over dt? Then v dt will be dx. If you integrate it, dx integration will tell you displacement is equals to v dt. So what this equation signifies? This equation signifies that integration means area, v dt means velocity time graph with the time axis gives displacement. Again, I'm repeating it once again. I'm reading it out again. Integration means area of what? Velocity time graph with time axis will give displacement. Can you read these things? Again, if I write equation, do you know that from the 10th class, I think I is equals to dq over dt. I is equals to dq over dt. You all know that. So what will become? dq is equals to I dt. Integrate it and you will get q is equals to integration I dt. So what will you read it? Integration means area of I versus time graph with time axis will give charge. So are you getting these things? These things are basic things and you need to know that. I hope it's clear to you. And it's a limit of time actually. Just do it in homework. There is a limit of time. I have just slowed it. This is again a homework. Take a picture of these two questions. Here we need to calculate the work done. So work done will be calculated by what? Area under the graph. So you need to calculate this area. Give me the answer in the next class. And here, this is again a simple question. This is a checkpoint of previous class. This is again a good question. You can easily solve it. Okay. Complete your work. And if you have any doubt, you can ask me out. Till then, bye.